Okay, thank you very much. All right. Let me start thanking the organizers for setting up such a wonderful workshop and for allowing me to be a part of it. Yeah, you see the big claim is already in the title, and I hope that in 1 hour you are convinced that what I'm claiming is actually true. So let me start with something that we probably all know. So this is now the single parameter pipeline of persistent homology that most applications follow. You have some data, maybe a point cloud, you build some filtration on this data, you compute your barcodes, and then the last step, which is usually the most difficult one, is you have to explain how you improve the understanding of your data using the barcode. And this, of course, depends on the application. Okay, so this has been used not countless, but many times. And the reason why this is so successful, in my opinion, is that the persistent homology as a concept has 3 major pillars. There is a sound theory based on applied topology, representation theory, algebra, and so on. On the other hand, there were many applications. So you probably have heard of the Donut database, which lists more than 500 papers where persistent homology has been used in practice. And the third pillar is the connecting layer between theory and application, which is algorithms. And I'm just repeating what Wojtek just said before the break. We need algorithms to compute all this nice theory that we are developing in order to make it useful in applications. And these algorithms are available and are used frequently. Good, so this is a single parameter. Now, I want to talk about multi-parameter. Actually, I admit most of the time it's 2 parameter. And yeah, there are reasons for considering that. In the first paper by Gunnar and Afra, they had an example where you have a data set and you increase the radius, you increase the scale, but also maybe you want to filter by curvature as an additional filter parameter. Then you have 2 parameters and you can look at the evolution of the shape with respect to both parameters. And one reason you might want to do that is outlier detection. So persistence is actually, we always say it's stable with respect to noise, but not with all kinds of noises. Persistence is very bad with outliers. Yeah? Outliers screw up your whole barcode. And you would, maybe before you use persistence, like in the picture on the right, you would like to classify some points as outliers and then use persistence only on the remaining points. But the problem is, for outlier detection, you have to say what is an outlier, and that usually depends on another real parameter that is called the threshold, what you classify as outlier and what not. And maybe you don't want to commit to a fixed threshold and you would like to look at all possible thresholds, and that's the second parameter. Yeah. Usually the density, like you look at the local density of a point, and if it's dense, then it's probably not an outlier, and if it's kind of isolated, you classify it as outlier. Okay, so that's motivation for using 2 and multi-parameter persistence. And yeah, so maybe 7 years ago, this is around 7 years ago, the situation was as follows, and I apologize, I make this joke already in many talks, so you might have seen it, but we haven't seen many memes in this workshop yet. So this is how I kind of looked at the situation. Yeah, there was a lot of research on the theory side, and like people have come up with many invariants, which is, it makes sense because we know that there is no complete discrete invariant like a barcode in multi-parameter, so you have to find something. Yeah, but then the applications of this were maybe a little bit neglected. So if you want a more scientific description, these 3 pillars, you had like substantial theory, not so many applications, some, but not so many, and also the algorithmic layer was very small. Yeah? So that means many of the invariants could not be computed, and this has changed since then. So what has changed is that we have now in the last years, we came up with a good amount of algorithms to compute many things that could be interesting in data analysis in the multi-parameter context. And yeah, this is what I want to talk about today. So my research agenda in the last years was to build a useful, solid algorithmic toolbox for multi-parameter persistence. And you see here some of the results we have achieved in the last 7 years or so. And I'll talk about 2 of them in more detail now. Just a little advertisement. Maybe this week you see enough talks already, but when you come back home, you can maybe, on YouTube there is an AATN seminar that I gave 2.5 years ago. You see I'm not very creative with talk titles, so this had the same title as today's talk. And it also has the same introduction and the same jokes and everything, but it talks about 2 different applications, 2 older applications that are in this list. But today I will talk about 2 more recent ones. The first is the Delaunay bifiltration. That's an extension of alpha filtrations that Gunnar talked about briefly today, an extension of this to 2 parameters. And the second part, I want to talk about graphcodes, which is an alternative way to represent 2-parameter persistence modules with interesting implications, as you will see. So this is joint work with my 2 wonderful students, Angel and Florian, and the first part also with people from Albany. I should mention these Angel and Florian look a little bit more stressed these days because they're just about to finish their thesis. But yeah, so this is joint work with them. And Florian, I should say, yesterday probably you ran away to dinner, but Florian in the AATN seminar just yesterday talked about graphcodes as well. So if you want a much more thorough introduction to this, again, you can, I guess next week or so, you can watch this on YouTube. Good. So let's talk about Delaunay bifiltration. So here's something that I guess everybody has seen. The standard model, how we explain persistence and why it is useful is we have a point cloud. We replace the points by balls of Bohr radii, and we track how the topology changes when you thicken up these balls. I call this the offset bifiltration, or union of balls bifiltration, not bifiltration, offset filtration. This is 1 parameter. Okay. Now, working with balls is inconvenient. We don't like that. For computational purposes, we want a combinatorial model. What do? We just take the nerve. Then we get the check complexes or the check filtration that you see here. And it's well known, the nerve theorem tells you this is homotopy equivalent to the offset filtration. Okay. You might like the Rips complex, the Artoris-Rips complex, which is a similar construction but not quite the same. The problem with Rips and check is that they are way too large to work in practice. When you have n points and you want to compute a check complex up to dimension k, you have n choose k or n choose k plus 1 simplices. Because everything eventually gets connected to each other. And that's for any reasonable size of n, this is just too large to do anything useful. And so what you should do instead is you should use Delaunay or alpha filtrations. The idea is, and Gunnar explained this already, so I go very quick. You look at the Voronoi diagram and you grow the balls, but you restrict every ball to its closed Voronoi cell. So this ball here doesn't grow beyond the boundaries of this Voronoi cell. And then you take the nerve of what remains. I didn't draw all the balls here, just 3 of them. And you see the advantage, like this ball and the ball down here, they will never intersect just because the Voronoi regions do not intersect. This way you get a much smaller complex, which is still homotopy equivalent. And it's, you can just, this is all well understood. So when d is equal to 2 and you're in the plane, the check complex has cubic size, whereas the alpha complex or Delaunay complex only has linear size. This is 3 over 2 rounded down. So this is cubic against linear, which is a huge difference. And this is not just some fancy theory that does not, like notation thing that is just not happening in practice, but this happens in practice. I see, even in this workshop, I still see many people that use Rips complexes for points in the plane, and you shouldn't do that. No matter how much you like Rips complexes, when you have Euclidean inputs in 2 and 3 dimensions at least, you should really use the alpha complex. side message I have here. Okay, but this is all well known, and this is one parameter, right? Now, two parameters. So we need some model, and I think a natural model for how you generate two-parameter filtrations is you have a point cloud plus a function on the vertices. And this function could be something like a density estimate. Yeah? Think of this outlier case from before. You just compute like a local density estimate and you get a function on the point cloud. It could also be something that comes with the application. Like maybe this is like, these are biological cells and this function is some sort of expressiveness of the cell in some form. Yeah? I think this appears often. I think we even saw in Gunar's talk there was a point cloud with a function appearing. Yeah? So I think this is a very natural model to look at. And yeah, good. Let me now forget about the function again, because what I talk about today, it will not depend on the actual function values. I just assume they are different. Yeah? But then I forget the actual function values, I just look at their ordering. Yeah? So I just take, this is this point with the smallest function value, second smallest, third smallest, and so on. Yeah? So what I assume here is just an ordered point set. Yeah? Ordered by some function value. Okay, so that's my setup, or you can also say it's a sequence of points instead of a set of points. And if you have this, you can build the function offset bifiltration. This is very natural. In the horizontal direction, you still thicken the balls by radius, and in the vertical direction, you include more and more points according to their function value. Yeah? You see here, there are some layers that I skipped, but you add more and more points, and then clearly this is a bifiltration. When you go to the right, it gets larger. When you go up, it also gets larger. Good, and we want to compute that. Now, for an arbitrary function, the task is to compute a combinatorial model for this thing. Okay. So the solution is, of course, trivial. You can just build the nerve everywhere. Then you get the function check bifiltration. Just apply the nerve. Same as we have seen in the single parameter case 2 slides ago. Nerve everywhere, everything nicely includes, and we are done. Yeah? Okay, but of course, this has the same problem as in one parameter, it's too large. Yeah? There is of course also a function WIPS bifiltration where you take the WIPS complex everywhere. This also works. Yeah? And this is actually how our story starts in this. I worked with Angel on function WIPS bifiltrations, and we did some work there. And you know, I like to rant about things. I try not to rant here on stage now, but my students see me more often and they hear me ranting, obviously. So one of my favorite ranting topics is what I call the unreasonable, sometimes unreasonable affection of the community to WIPS complexes. I mean, it's okay. I mean, Wojtek said he likes WIPS complexes. I also like WIPS complexes, but sometimes I would say people like them a bit too much. Yeah, as I just said before, they use them for Euclidean problems in the plane. Yeah. So anyway, Angel took this very seriously, and he said, well, you know, function WIPS is nice, but there is also function check, right? And I said, yes, there is function check, but it's too large. But now he asked me, why is there no function alpha bifiltration or function Delaunay bifiltration? Just like we saw 2 slides ago, yeah, you should use alpha instead of check. And yeah, I was answering, yeah, why isn't there? Why don't we do that? Yeah? So let's do this. I mean, it's very simple, right? Just take, instead of the check complex, you take the alpha complex everywhere. Yeah? And you go larger, and you have something which is much smaller everywhere, and you have the function Delaunay bifiltration. Yeah? That was simple. No? Any remarks about that?
We don't have inclusions.
Exactly. Yeah. Okay. Yes. We cannot fool you. I see that. Yeah, this doesn't work, right? So look at this. For instance, look at this triangle here. That's the Delaunay triangle. To remind you, the Delaunay triangle means the circle of the triangle contains no other point, right? So this is clearly empty. Yeah. So this is the Delaunay triangle. But when you go up here, you have included these 2 points, and they destroy this triangle. So this triangle is not there anymore. Yeah, so there's no inclusion in the vertical direction. Yeah. Okay. So we are set for a little moment. It's a small set phase because, of course, the actual contribution of us is that we still find a way to well define such a function Delaunay by filtration. And the idea is this: so we build something which is called the incremental Delaunay complex. The idea is that we have a complex that contains all Delaunay triangulations of all prefixes. So it contains this Delaunay triangulation and this one and this one. But you cannot just take the union of all of them, because when you take the union, you introduce some holes, some voids in the middle. And so you change the topology. So the trick is that we add tetrahedra to triangulate these holes in between. Yeah? And this sounds maybe a bit complicated, but you will see on the next slide there is an astonishing simple algorithm for building these tetrahedra. Okay, and then we have a complex that contains all Delaunay triangulations, but that's not enough, because you have to also assign the right filtration values, because you want the filtration to be equivalent. So when I go here, when I go in this position, I want to pick, for this bigger complex, I want to pick the filtration value such that the subcomplex here is homotopy equivalent to this picture. And this should be true at every position. Yeah? So there are 2 steps: defining the complex and finding the filtration values. So I talk first about part 1. How is this complex defined? So here's the whole construction in 4 lines. To understand that, it is helpful if you know about how Delaunay triangulations are constructed in an incremental fashion. So this is Computational Geometry 101, but I'm not sure everybody here has taken a course in computational geometry. So here's a picture. Can you see that? Should I switch on the light, or is it fine? I think it's good enough, right? So let's say we have already the Delaunay triangulation of some points, and we add this red point to it. Yeah? So the flip algorithm that I will briefly outline is now the following. You get a new point. So you first look for the triangle that contains this point, and you just split this triangle into 3 subtriangles using this new point. Now you have a triangulation that contains the new point, but of course it might not be the Delaunay triangulation. Yeah? So you have to do more work. And the thing is now this: you get these 3 new triangles and you check whether they're Delaunay. And in this case, this triangle that I marked here, that's clearly not a Delaunay triangle. I mean, when you build the circumcircle, you can see this is very large and it will contain this point. So it's not empty. And so this is not the right triangle. So what you do is then, you look at this edge, which is away from the new point, and you flip this edge. That's why it's called the flipping algorithm. So you replace this edge with the opposite edge that we see here. And it is actually, no, it's not obvious, but true that then, well, let me say it very roughly. I don't want to spend too much time on this. You get closer to Delaunay by flipping this edge. Yeah, you might not be Delaunay because now you have to flip maybe this edge or this edge, and you have also to check the other edges. But there is a well-defined procedure how you get to Delaunay triangulation just by this operation. Yeah, by flipping. There is a local test. You flip the edge, and eventually you will find the Delaunay triangulation. Okay, but I just want to concentrate on this one flip. So what has happened here? Before I flipped, I had 2 triangles. I had the one I marked and the opposite one. And after the flip, I have this triangle and this triangle. So these 4 triangles together, they are the boundary of a tetrahedron, or a flat tetrahedron, which is spanned by these 4 points. Let me mark it like this. Yeah. These four points that you see here, they form a tetrahedron, and I just, whenever I flip an edge, the flip corresponds to a quadrilateral, which corresponds to a tetrahedron. So whenever I flip an edge, I add this tetrahedron to my incremental Delaunay complex. And that's the whole thing. That's all what we have to do. We just incrementally add points one by one. We apply the flipping algorithm and we add this tetrahedron. That's the definition of the complex. Okay. And the good thing is, because it's so simple, all the work has been done. We can ask now, how big is this complex? And of course, the complex is as big as the number of flips that we perform, because we have one tetrahedron per flip. The number of flips has been analyzed in the 90s. This is this number here. Sanity check, if d is equal to 2, we get n to the 3 over 2 rounded up. So this is n squared. Yeah, so the complex has size n squared in the plane. Now, maybe this is a bit odd if you know this algorithm already. What you might have learned is, the number of flips is also the running time of this algorithm, of course. Yeah? And this is an algorithm to compute Delaunay triangulations. And when you heard about this, you might have learned this is an n or n log n algorithm, more precisely. So this is not quadratic, it's a linear algorithm. So this sounds like contradicting what I wrote here, yeah? Because I say it's quadratic, whereas the running time of this is considered to be linear. The most likely explanation would be that I messed up the rounding, but I didn't. Yeah? I can assure you this is really rounded up. The question is, where does this come from? Does anybody see where this comes from? Why we get quadratic, not linear?
In the order n flips for each increment.
Yeah, in every increment. So the point is this. So I did not say one thing. So this is computing Delaunay with this algorithm is n log n, but it's only n log n in expectation. If you remember, it's maybe a long time ago, but what you have to do is you have to shuffle these points first and then add them in a random order. And only in expectation you get the number of flips is n log n. So this is this famous concept of randomized incremental construction in computational geometry. Yeah? But the problem is we cannot do that here. We cannot shuffle our points because remember our points are sorted and we have to add them in the right order. Otherwise the complex is not the right one. So we cannot use randomized incremental construction. And so in the worst case we have quadratic time. But in practice this doesn't really happen. Yeah? We still have usually, we made extensive tests and this is never much bigger than the Delaunay triangulation itself, which is of linear size. Okay. Yes, okay. So some other remarks. Instead of, maybe you didn't learn the flip algorithm, but you learned the Boyer-Watson algorithm, which computes conflict zones and then retriangulates the conflict zones. You can equally simple define our complex in this way. This is actually the algorithm that Seagal uses, that's why it's important. We can also, if you don't like these algorithmic definitions of a complex, you can also define them as a variation of empty circles. I will not go into that. And last but not least, there is a beautiful interpretation of this in terms of parabolic lifts. You might have heard that if you have a point set in the plane, you can lift it in 3 dimensions to the paraboloid. You take the lower hull of the points, and that's a lift of the Delaunay triangulation. Now if you have this lower hull before you add a point, and after you add a point, then the lower hull afterwards is below, because you add a new point. Yeah? So you get actually two lower hulls on the paraboloid, and one is lower than the other, so their union encloses a void. I hope you can imagine that. Yeah. So the union of before and afterwards encloses a void, and these tetrahedra that we add here, they are exactly triangulating this void in tree space. So that shows you that this incremental complex is embedded in d+1 dimensions. Yeah. And this interpretation also helps you to see the homotopy equivalences that you have to prove. Yeah. So this is actually a very nice interpretation of this. Good, so this is the complex. Now, remember, there is a second part. We have to also assign filtration values for everything. Also here, there is a very simple solution. For every simplex, you just take the points that span it, and you take the minimum and closing wall of these points, which is exactly the check radius of the corresponding simplex. So you just pretend this is a check complex, and you just compute the check filtration values there. This might look strange, but the reason why this works is, for the single parameter case, it has been shown by Bauer and Edelsbrunner that you can use the Delaunay. You can use the Delaunay triangulation, and every simplex in Delaunay triangulation, you just assign it a check filtration value, which sounds like you do the wrong thing, but they show this is equivalent. Yeah, and we can just extend this to our two-parameter case for order points. It becomes a bit technical, but and actually it uses discrete Morse theory, but we can show that their result extends also to our case. And so using just the check radius is fine, which is good because computing minimum closing balls is a standard problem, and there is fast software for this. So that means we don't have to do much because everything is already there. We can use CR to compute the Delaunay triangulations using this conflict zone algorithm. This way we get our tetrahedra very simply. Then we compute the minimum closing balls using some other software by Gärtner. And then we just throw all the tetrahedra in GUDI, and this will generate the complex for us. And so when I coded this, it really took only 200 lines of code to write the whole thing. Of course, 200 lines of code using these libraries, which are much bigger. Yeah? But it was very, very simple. The code we have now is a bit longer because we optimized here and there. But let me show you. You know, this is. I claim practicality, so I should at least convince you that this is doing something. And I'm fully aware of the risks of doing such things live. So let me first, maybe before so here's the data set that I will use today. So these are 8,000 points sampled from the sphere in R3. I just show you the first 10 of the 8,000 lines. You know, this just, the input is very simple. You just have 3 coordinates. And the last thing is the function value. Here we computed some density. And we negated it because we want the densest points to come first. So they should be the smallest. Yeah. So that's the input. So we have 8,000 points in R3. So let's compute now the thing I just talked about. Okay, so this computes now the Delaunay bifiltration. Okay, so this took, there's a lot of output. I show you what you should look at. This took 4 seconds. And here, here are the simplices that are created. So 8,000 points, 160,000 edges, and so on. And of course, also, this is a 3-dimensional picture, so the holes that we have to fill out are 4-dimensional now. Yeah. So, and you see, this is like, I don't know, do I add up 1.5 million simplices that were generated? And we can look at how big is this file. Yeah, around 100 megabytes created in 4 seconds, which is nice. Now, as I'm on it already, let's see. I mean, this is demonstrating this part. But now you can ask, what do I do with this bifiltration? Yeah. Let's compute some homology of this. So this is now. Maybe I show you also how this file looks like. Okay, so it's just again the first 10 lines. The file is obviously much longer. So this is a chain complex, yeah. So this is a chain complex format that we defined. It's bifilter. This is this 2 here, and here the number of simplices in all like the number of generators per level, per dimension. And then here's just a long list of. This is the byte rate where the simplex or the generator enters the chain complex, and here is its boundary encoded in some format. Yeah? So this would be, the 4 simplices come first. That's why they have these 5 boundary elements. Great. Yeah, so maybe now we want to compute the homology in dimension 1, let's say. And there we compute a minimal presentation of this. So this is the MP3 library that we wrote some years ago with Alex Rolle. So let me do this. It's a bit weird. We want H1, but I still have to say dimension 3 because I want to compute the minimal presentation for this part of the chain complex. So this starts at the third position. Yeah? The interface certainly is not the most intuitive one. But still. So let's do this. And let's write this into minimal presentation. I forgot the mind. Okay. Let's do this again so you see that it actually, you see the time, but you saw it took 3.5 seconds, yeah? And it has generated now minimal presentation with 28,000 generators and 41,000 relations, yeah? Okay. Now we have now represented H1 of these 8,000 points on the sphere. And now let's say, I mean, we know every persistence module decomposes into indecomposable elements in a unique way. Yeah? So maybe we want to look at these indecomposables, and there is yet another software which was written recently. I'll say a few words in a second. So it's called AIDA. AIDA computes the indecomposables of this. Okay. So, a few words about AIDA because I will not talk about this in detail. This software is written by another of my brilliant students, Jan Jendrisiak, and he presented this at Sausage this year. This is joint work with Tamal, myself, and Jan. And so this is based on a reduction algorithm by Tamal and Xin, and we extended this to the general case and also introduced many heuristics for improving this. So this takes a while now, and you might be disappointed because it looks like a rather small matrix, at least in CDA context. But this is not just a straightforward Gauss elimination algorithm, right? This is a very, let's say, sophisticated matrix reduction algorithm. It needs row and column operations and actually very complicated. I mean, the task of computing indecomposables is a very complicated one. Yeah? So this takes a little bit of time. I forgot to measure the time now, but if I'm not mistaken, this should finish rather soon. Yes? Okay. So you see now it has finished. This took around a minute, yeah, let's say. And it has computed now, okay, this consists of 22,540 indecomposables. There are 1,052 non-intervals in there. And of course it has also, like, you can now look at the output file and you can see all the indecomposables, yeah, if you want to. So this is, all these steps require a lot of algorithmic engineering, yeah. So none of this was possible a few years back. Neither computing such bifurcation, I mean, you could of course in principle just use the check version of the bifiltration, but for 8,000 points in R3, good luck, yeah. This will not work. It's just too big to even store this on your hard disk. Yeah? And computing minimal representation is a crucial step, and of course this decomposition was also not there before. Yeah? So these are all things you can do with today's software. Good. So, and all these softwares that I've used now, you can download them and use them. Yeah? And this, maybe one more word about this. I'm fully aware that it's not so easy to use them. They're all C++ libraries and the interface is a little bit suboptimal. But if you want to use them in some practical scenarios, you can always, of course, contact me and I can help. Yeah? I'm very glad to provide support there. Good. All right, so far, then let's switch to part 2, the graphcodes. Yeah, so the setup here is this. I have a general bifiltration, for instance, what we have just computed before, or something else. I assume for simplicity everything is simplicial, and it's a real bifiltration. No quasi zigzag, no simplicial maps, nothing, just inclusions. And for the experts, I assume one critical. If you don't know what that means, it doesn't matter. Yeah? It will not really appear in the talk. So here's now what the graph code is. This is, I think, a rather simple concept. We look at our bifiltration and we just ignore the vertical arrows for a moment, and we just look at horizontal slices everywhere. And in a horizontal slice, this is a one-parameter filtration, and in every horizontal slice I have a barcode that I can compute, or equivalently a persistence diagram. Now I like to represent them as persistence diagrams. So I have a stack of persistence diagrams. Okay. Now I want to also put the vertical arrows into account. And what I do is I choose for every persistence diagram, I choose a basis. So every feature here, every dot in every diagram corresponds to a homology class, and I can pick a representative cycle. And I just make a choice. I pick for every of them, I pick a cycle. And then of course what I get is I get the cycle basis for the final complex here, everywhere. Yeah? So okay, so I can look at one cycle here, and so this is a cycle somewhere here, and I can just include it in the upper row. And of course, because I have a basis here, I can express this cycle as a linear combination of cycles in the upper row. Just straightforward linear algebra. And I can then say, like, if this cycle here is, let's say, this cycle plus this cycle, I just connect this dot with this dot and with this dot to express this cycle maps to the sum of these two cycles. Yeah? So once I fix basis, I can do that, and I just do this everywhere, and that's the graph code. Yeah? It's just the stack of bipartite graphs connecting two consecutive layers. I should maybe more precisely say this is a graph code of the bifiltration because it depends on the choice of basis. If I take a different basis, I get different edges. I get the same nodes, but I get different edges. Yeah? So you see already, and this is what every reviewer tells us whenever we submit papers there, this is not an invariant, and we know that, of course. Yeah? We emphasize this in the paper as well. This is not an invariant. It depends on the basis. Yeah? So this is something that you might consider as a weakness, but it has also many advantages. It's a simple description of the module actually induced by this bifiltration. It's very visual. You can see what happens here. Kind of, it's an embedded graph, right? It's very efficient to compute, and this is not obvious. You can, in fact, compute the whole graph code with a single matrix reduction on the big complex. So computing this whole thing is not more expensive than computing the barcode of the upper row, which is usually quite fast. Yeah. And the last thing, which is also maybe the most important thing, yeah, it's a non-invariant, but it's a complete non-invariant. Yeah? In the sense of all the information of the persistence module is encoded in the graph code. And in this sense, it's an alternative to presentations, or minimal presentations, because also presentations are not unique, but a module can have many presentations, but every presentation captures the whole module. Yeah? So this is the graph code. Now, why should we be interested in graph codes? The first reason is, this is how we started with this. This is very useful or very directly applicable in machine learning contexts, because the graph code is a graph, and there is this thing called graph neural networks. Like usually, neural networks like vectors to work with, but there is also the possibility of just feeding it graphs. So we can just say, okay, I just throw my graph code into a neural network and let it solve its classification task using this. And I think this is very satisfying because you don't need any vectorization. Because when you make a vectorization, this is the standard way of using machine learning. Here you use use krill or generalized rank invariant or persistent images or multi-landscapes or whatever. You always make a choice because you have your module and you select partial information and you say this is the information that the machine should look at. But with graph codes, you don't have to do it. You just give the machine the whole thing. And it makes sense because as soon as you use a neural network, you lose control what the machine is picking on, right? So why don't you just give the machine the whole thing and let the machine decide what is the most relevant feature? Yeah. And of course, I mean, I should say a graph neural network, when you look at it, it picks some vectorization, right? I mean, but the vectorization is then internally. It's not in your control anymore, but it's delegated to the machine. Yeah. I guess you can see this as an advantage or disadvantage. Yeah. Okay, but that's, I mean, and I'm just saying here in 2 lines, just throw the graph in a neural network. Of course, you have to build some sort of meaningful architecture, how you do this in practice, and I will not talk about this because Florian did this part and I don't fully understand it myself, but it works. And I want to demonstrate, we have one particular experiment which I find it very interesting. We generated some data which has a clear topological signal. So we pick I and we sample I annuli and 5 minus I disks in the plane, making sure they are nicely separated. And then we put some uniform noise to make it more difficult for the machine. And the task for the machine is to guess what was I. Yeah. And in this picture, I'm assuming you have a good guess what the I actually should be. Yeah. So it's not a very difficult task, but for a machine, maybe it is difficult. I should mention, we also, well, let me first show the result. So the result is this. This is, like Kamal has already introduced, or he did that, he's mentioned all these previous. This is multi-parameter images, multi-parameter landscapes, and others, and Grill is also here. And here's graphcode, and you see the classification results in graphcode for this particular kind of example performs quite a bit better than most other methods. And the second line shows you the time that was needed, and because graphcodes are so efficiently computable, this also works a bit faster. I should mention also Grill performs pretty well. And this time, this is an older version of Grill, yeah. So Tamal shakes the head. So this, it's faster by now, yeah. I'm sorry, maybe I should have blacked out this number, yeah. But okay, it was back when we tested this, it was like this. Okay. I should also say, we also in the paper, we tested these graph instances that Tamal was talking about, and this is how we started actually. But yeah. I will not rant here, but we were a bit unsatisfied with this graph data set because it looks to us like these graphs do not carry any topological signal. And so it is not so clear whether you should use any of these methods on these graphs, because if there is no topological signal, why would topological methods work? And here, this is like a proof of concept. There is a clear topological signal, and so these methods should actually perform pretty well here. Yeah? Another point is, I don't blame the authors of this to use the graphs, because that was the only thing that was really available. The reason is, this here contains 5,000 points, and this was not possible to be computed before. Of course, what we used for computing this was the function Delaunay from the first part. And this was just available for a few months when we did these experiments. Yeah? So this is just another illustration of now we can actually handle fairly large point clouds and feed machine learning applications with point cloud data. And this was not possible when you use whips or check complexes, or just with a few hundred points maybe. Yeah? So this is, I hope that we identify more, maybe also real world point cloud data sets that clearly have a topological signal, and then we can reevaluate all these methods using these data sets. Yeah? This is a question for the future. All right, so that's the machine learning part. Now then, we also realized graphcodes, they can also reveal certain structure for algorithmic purposes. And here's the first fact. So you can compute a graph code choosing an arbitrary basis. If you are lucky, then your graph code is disconnected. The graph splits in connected components. And then it's immediate, almost trivial, to see that every connected component corresponds to a summand of your decomposition, of your module. That means the graph code gives you a method to partially decompose your module into summands. there is no reason to assume that any of the sums is indecomposable, but it gives you a partial decomposition. This could be very helpful, yeah, or useful. And but of course, the question is whether this happens, and spoiler, this always happens in practice. Yeah, like the graph codes split in all examples we tested, split in many components. Now, if you are even more lucky, then you might have a component which consists of a path. So it's just a bunch of edges going upwards, and then you can quite immediately observe that this is an interval in the decomposition, because it's basically a stack of intervals, of 1 parameter intervals stacked together. This is an interval in 2 dimensions. Yeah? And of course, then you know also it's indecomposable, because intervals are indecomposable. And also this happens a lot. You will find this a lot. So you will be able to detect many intervals just by computing a graph code. The third observation is a little bit more involved. So, I mean, if you are very, very, very lucky, all your components in the graph code will be such upward paths. Then you have, of course, then you know that your module splits into intervals. It's interval decomposable. Now, this will not happen in practice. You will not be so lucky. Yeah? But the other direction is also true. If your module is interval decomposable, you will find there is a choice of bases you can pick such that your graph code splits into paths. Yeah? That's maybe not obvious, but it's quite easy to prove that. And so we thought maybe there is a way to compute such a basis, or the question is there the question of whether there is such a basis will be an algorithm to decide whether your module is interval decomposable. And that's what we did. So we found an algorithm to decide whether a persistence module is interval decomposable in n to the 4 time. And if it is, it also gives you the decomposition. Now, how does this work? So maybe just give you the rough idea. So there is one way of looking at persistence. So when you have a persistence module, you have these maps in between, right? So okay, these are matrices, and well, I write this standard reduction, which is maybe not what most people understand as standard reduction, but one way of computing persistence is you change the bases of the VIs, and this induces row and column additions on the matrices, and you make sure that all these matrices are in Smith normal form. And once you have done this, then you have computed the barcode. Yeah, this is I write a standard way of computing persistence, at least in a theoretical setup. Yeah? And the way you do that in standard persistence is this: you are allowed to use any left to right column addition and any bottom up row addition. They are all allowed, and it's always possible to bring all these matrices to Smith normal form. Yeah, because there is always a barcode. Okay, what changes here is this: when you have graph codes, you can also draw such a picture, but you don't have a persistence module of vector spaces, but you have a persistence module of persistence modules. So everything here is a persistence module itself. And the effect is, in simple words, you cannot use all of the column operations anymore. There are certain left to right column additions which are not allowed anymore, because you have a more complicated structure here. Same for row operations. So that means you want to bring it to Smith normal form, but you have only a subset of the operations is allowed. Now so what we do is this: we just define one algorithm which tries to bring it to normal form. And if it manages, it only uses valid operations. If it manages, then clearly you found the interval decomposition. That's the simple direction. The hard direction is the algorithm might get stuck, and then it just says, I cannot do it, so it says not interval decomposable. And the hard part is to prove that there is no other path, that you could maybe use another set of row and column operations such that you would get interval decomposability. Yeah, so this is the difficulty of the algorithm. Another remark, n to the 4 is the running time. Actually, in the paper with Jan and Tamar, there is even an n to the 3 algorithm for the same problem, which works very differently. Yeah, so this is not even the best possible, although I would conjecture this algorithm actually runs in n cube time. We just failed to prove it. Yeah, it doesn't look like it's really. I mean, it's a worst case analysis. Yeah, but I think we'll just miss one idea. Okay, so let me show you this as well very quickly. So let's compute the graph. So remember, I just continue on this example. So this was this 8,000 points with 22,000 indecomposables. And let's compute the graph code here for the minimal presentation. So it's still H1. And I have to say output decomposed. This just means take the graph code, compute the connected components, and for every connected component, convert it back to a minimal representation again. Yeah, this is what will happen here, and the output will be a partially decomposed module. Okay, so I start this now, and it's done. This took less than a second, and you can see the total number of components of the graph code here is 21,124. That means the vast majority of components is split off in less than a second. Yeah. Okay, but it's obviously not all summons are indecomposable because we know it's 22,000 something indecomposables. Yeah? But now you could say, as an application of this, you could say, okay, now I can just use AIDA, the full decomposition algorithm, and I just apply it on every of these 21,000 indecomposables, right? So let's do that. I just call AIDA. And let's do time. So this is the file we just computed with the 21,000 instances. And maybe find an output file. I think this works. Okay, now AIDA runs 21,124 times. And remember, I took a minute before, and now it only took 10 seconds, and of course, it has now split some components, and it gives you the same number of indecomposables. That's good. The same number of non-intervals. It gives you the same decomposition, of course. Yeah. Yeah. So you see, this is already one application for these graph codes. You can just pre-process the file, split, like partially decompose it, and then AIDA can do the rest if you really want a full decomposition. I should mention, though, that this is a cherry-picked example. So we tested this extensively, and not for all instances it is that helpful. I mean, now the running time reduced by a factor of 6. In some cases, it doesn't really help. And annoyingly, in some cases, it even gets worse. So sometimes AIDA takes longer on the partially decomposed outputs than on the full output, which is a bit counterintuitive, but it still happens sometimes. Yeah. Anyway, so this was just a little demonstration of what is possible with this software. So to recap, the first point I already made. So now with this Delaunay technology, we can generate 2-parameter filtrations for reasonable sized point clouds, and I hope this will lead to good benchmark sets for instance, testing machine learning vectorization methods and so on more thoroughly. One point I want to make is that computational geometry has a lot to offer in all these optimization procedures. I mean, it's pretty obvious in this Delaunay project that geometry was important, but sometimes you find geometric techniques to be useful also in very abstract algebraic setups. Yeah? So I can only recommend that you should, if you haven't done so, you should learn computational geometry because it is very helpful in this context. And finally, the big point is, the algorithmic layer of multi-parameter persistence is growing, but now the application layer is also growing. But I hope that with all these new techniques for computing things, we also find more good showcases for using multi-parameter in practice. Yeah? So to grow the application layer as well. And that's it. Thank you.
So you had this filtration, and you started by doing one parameter persistence on all of the rows, for example. You could have started in the other direction instead.
Right.
Can you comment on that?
Yeah, of course, you could also take vertical slices and then connect them horizontally, and you get a different graph code. We did it such that the primary parameter is scale, so that the slices are scale-based filtration, so radius going balls. Yeah. This appeared more meaningful to us. I'm not even sure. I think Florian tried once classification based in the other direction, and it did not work so well. And this combined with our perception that this would be a bit weird to do, we did not follow more on that. But I mean, you could in principle even look at like diagonal graph codes, right? I mean, it is. I mean, when you have non-straight slices, you can still connect them somehow. The algorithm gets more complicated. So I would not claim anymore that we can compute it so efficiently, but you can certainly also define it.
Yeah, so we all know since the very beginning of GA that for low-dimensional Euclidean spaces, Delaunay complexes are way better than red complexes. And
do we all know? I hope so. Yeah.
In principle, we all know. What do you think? Why is it so late that someone looked at Delaunay calculations? And it's a quite reasonable thing to look at. I
agree. Like my student asked me the question, and also I had the same thought process. Like, why has this not been done? Yeah, I have no good answer for that. I don't know.
Just a quick question. So, graphcodes using Z2 coefficients for the modules?
I forgot to say that it's all like Z2. You could have arbitrary coefficients, then you have, I guess, to write the coefficients on the edges. Yeah.
So that you need to label then the vertices, right? With some coefficients scalars, or
no, then the linear combination you get is like with coefficients, and you have the edges. I guess the edges are then labeled with the coefficient.
Then so that it maintains complete.
Yeah, yeah.
We have a question about the graph code. You mentioned the construct on the graph code, it is different up to how do you choose the basis, right? And if the graph code has several components, then the precision module can have the direct sum. And I think reflect how it is different, you choose different bases of the graph code.
Well, if you choose a different basis, you might get different components. But of course, it's not arbitrary because the components are kind of like given by the structure of the module. Yeah. We tried things like iterating the construction. Computing the graph code, getting the components, and then on every component, doing graph code again, and maybe with a different basis. I think you need a different, you can shuffle the bases in some way. This didn't work well. I mean, it splits off more components, but one problem is that when you take an arbitrary basis, you lose sparsity. And then the graph code gets like, you get basically not a complete graph, but you get a very dense graph, and then this is bad for the performance. I'm not sure this really answers the question.
I think so. I have one more question. So if a graph code, so suppose it is connected, and if you can find some way somehow to measure how difficult to depart it into two parts, like trivial constant, something like that, then can this reflect somehow how difficult to decompose the precision model somehow?
Okay, I'm not sure there is a connection, but certainly you can certainly think of heuristics of kind of looking at the graph code, identifying features where you see, okay, if I just change the basis a little bit here and there, I can split these two. This is certainly an idea we had and we did not really follow, but this like a heuristic of simple local changes in the basis that might make the graph code nicer. That means more decomposable or sparser or whatever. This is something, that's an interesting question.
If not, thank you very much again. And this is the end of this session, morning session.
Yeah.